Okay, so today we're going to be talking about Unit 3, Part 2. This is about forces and how those forces come into play with determining liquid and solid properties. So we have two types of forces. You can have intermolecular forces or you can have intermolecular forces. So intramolecular forces are within a molecule. So say we have NaCl, it would be the ionic bond between Na and Cl. So it's within a molecule. So that would be the types of intramolecular are ionic, covalent, and metallic bonding. So they're stronger than intermolecular. That makes sense. So it's harder to break apart a force within a molecule. It would be harder to break apart the ionic bond between Na and Cl. So intermolecular forces, the second one, they are between stable molecules. So this is like two molecules. So say we have H2O and another H2O. So the force between these two. So these tell us the difference in physical properties that we have. So they are the reason we have liquids, solids, and gases, and they're going to play a big part in this unit. So ionic bonds can be either intramolecular or intermolecular. So as intramolecular bonds, so the bond within the molecule, they are stronger than the intermolecular forces. But we also have ionic forces as intermolecular, and it's what's going to dissolve the salt and make salt water. So just know from this slide that they can be both intra and intermolecular forces. So we have four types of intermolecular forces that we are going to focus on in this course. And this is just an overview of them. Dipole will be the attractions between opposite charges in polar molecules. Polar being a big thing, so it has to be polar to have a dipole. Dipole. Also, dipole is also known as permanent dipole. Okay, so we have next ion dipole forces. So this is between an ion and a polar molecule. So the example that was given was NaCl. When it's dissolved in water, you have the ion Na and water, which is polar, making an ion dipole force. We have hydrogen bonding. This is going to be the strongest type of dipole attraction that occurs. And it's only when you have HO, HN, and HF. So you have to have N, O, or F bonded to hydrogen for it to be hydrogen bonding. So dispersion forces, this is called instantaneous dipole. This means that the dipole happens for a second. So this is going to be all molecules that dispersion forces will happen in. And the larger the molecule, the larger the dispersion force. Okay, so we have the energy line for intra and intermolecular forces. So this compares the energy of the type of forces we have. So as we can see, intramolecular forces are higher when compared to intermolecular forces. Okay? Oops. Let me see something real quick. So this is our first smiley face within the slides. So that means that it's going to be seen on that first exit ticket you take over this unit. So intramolecular forces are ionic bonds, covalent, covalent double, and covalent single. So see with covalent, as we add another bond, it increases. And then ionic bonds being the highest. Ionic bonds being the highest. Ionic bonds being the highest. So then we have intermolecular force. So hydrogen bonding is the most. When compared to dipole and dispersion forces. So dispersion forces are extremely low. And then we have dipole, which is polar molecules, is 5 to 20. Okay, moving on. So, as I said, dipole is between polar molecules. Only polar molecules can be dipole. So the asymmetrical molecules, meaning that they're not the same if you cut it in half, will have a permanent dipole. So if we look at CF4, it's symmetrical. If you cut it in half, you're going to have 2 fluorines on one side, 2 fluorines on the other. This means that it has no net dipole moment. So it is not dipole. It's actually dispersion forces at work, but we'll talk about that later. If we cut this CCl3H molecule in half, we have 2 Cl's on one side, 1 Cl, and 1 H on the other side. So it's asymmetrical. Asymmetrical, meaning it has a permanent dipole. Okay, so giving dipole interactions. They only exist in polar molecules, also known as asymmetrical molecules. Dispersion forces. These are going to be in symmetrical molecules, like we saw in the last one. C, Cl, 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 and Cl. If I cut it in half, I have what I have on one side, I have on the other, making it symmetrical. So they don't form a net dipole all the time. So they don't have a permanent dipole. But if for a second they form a dipole. So that's why we call it instantaneous dipole. It's just for a little bit. So when you talk about dispersion forces, they're also known as London forces or dispersion forces or instantaneous dipoles. And they happen in symmetrical molecules. So the electrons move randomly in a molecule and the molecule will become polarized. In that moment, so in that instant, that second, they form an electron cloud, giving them a dipole moment just for a little bit. So a key thing to remember, so star this, when molecules increase in size, they are going to have a larger dispersion force. So say we have CCl4 or XeF4. They're both symmetrical, so they both have dispersion forces. But XeF4 is larger than CCl4. So it is going to have a larger dispersion force, a greater intermolecular force. That's what IMF means, intermolecular force. They have more electrons that can participate in the force, making it a larger force. Okay, so again, dispersion force is continued. Symmetrical molecules can only have dispersion forces. But all molecules will have this force. All molecules have this. Okay. Again, we see a smiley face, so pay attention to this slide. So symmetrical molecules have dispersion forces, but also asymmetrical molecules have these forces as well. So they are the dominant force that you'll see. Every molecule will have dispersion forces and could have more, but also could just have dispersion forces. And as we see, the molecules get bigger. So we go from methane, which has 1 carbon, to pentane, which has 5 carbon. They increase in boiling point. So we go from boiling point being negative 161.5 to boiling point being 36.1. So we have an increase in boiling point because we had an increase in mass, which gave us an increase in dispersion forces. So we have hydrogen bonding. This is going to be one of the strongest ones that you see. And again, hydrogen bonding can only happen when hydrogen is attached to nitrogen, oxygen, and fluorine. These are associated with larger electronegativity differences in small atoms. So this makes the hydrogen bonding significant. So we're going to see why when hydrogen is bonded to carbon, why it's not hydrogen bonding. But with hydrogen bonding, the molecule that contains hydrogen, so we're looking down here right now, the molecule that contains hydrogen will form a hydrogen bond with the molecule that has a lone pair. So if we look over here, water has hydrogen bonding. The hydrogen will bond to the oxygen, which has a lone pair, forming a hydrogen bond. So again, water and ammonia, N to H, that's a hydrogen bond. Hydrogen will bond to the nitrogen, which has 2 lone pairs. Then over here, hydrogen fluoride, again, hydrogen to fluorine, one of the options. It bonds to the one of the lone pair. And so on, hydrogen to oxygen. So how we figured this out is we looked at the boiling point of hydrogen molecules. We saw that H2O, HF, and NH3 had extremely high boiling points when compared to other hydrogen molecules. It was significantly different. So they were wondering, like, why did that happen? So it turns out that their hydrogen bonding is more stronger in intermolecular force. So this is why only nitrogen, oxygen, and fluorine can form a hydrogen bond. Just because you have a hydrogen in the molecule, like HCl, does not make it a hydrogen bond. So hydrides have a lower boiling point when compared to those nitrogen, oxygen, and fluorine. So meaning they have a weaker IMF. That's why we don't classify them as forming a hydrogen bond. Hydrogen bonds are strong, so that's why nitrogen and oxygen and fluorine can only form a hydrogen bond. So then we have hydrogen bonding ranked. So we have HF, OH, and NH. So HF being the strongest. HF is the strongest force. So this is because we look at electronegativity. Fluorine has a larger electronegativity, so HF is going to be stronger than OH or NH. Then we look at when hydrogen forms multiple bonds. So H2O will then move up to being the strongest. Okay? And then followed by HF, then NH3 being the weakest. OH bonding is also important in biological compounds. We see OH bonding in carbohydrates. They're made up of multiple hydrogen bonds, and this is why sugars are so sticky. So IMF explains liquid properties. With increasing IMF, the following properties increase.